This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Speaker is Kasidit Srimahajariyapong, and he's going to talk about connecting phases of matter to the flatness of the loss landscape in analog variational quantum algorithms.
Okay, go ahead. Good afternoon, everyone, and thanks for your introduction. My name is Kasidit Srimahajariyapong, so it's quite a long surname. I am a master's student from Chulalongkorn University, and today I'm going to present my recent work with Chiprat and Supernat in connecting phase of matter to flatness of the loss landscape in analog variational quantum algorithms. So for the overview of the talk that I'm going to say is we connect the phase of matter in analog quantum simulator to the flatness of the landscape by studying the analog VQA ansatz initialized into phase of matter, that is tumuli phase and MBL phase, or many-body localized phase. And then we study the expressivity and the trainability. So in this talk, there will be the Barren plateau again. Okay, so for completeness, let me talk about the variational quantum algorithms. So VQA is a class of hybrid classical quantum optimization. It's optimized quantum dynamics to minimize cost function, and it has a problem known as Barren plateau. And to do something with the Barren plateau, we can select the choice of unitary, or we can try to initialize it in the careful way. And in our work, we particularly interested in the representation of the ansatz in the analog representation. So the quantum dynamic will be something like the Hamiltonian evolution that inherit from the quantum device instead of the arrangement of the quantum gates. And the reason that we are interested in analog quantum simulator representation is that we know that analog quantum simulator require less control to implement the VQA ansatz. So it's more suitable for the near-term quantum device. And second, it's relatively less exposed in the context of the VQA. And lastly, it can connect with quantum phase of matter much more easier than its digital counterpart. So this somehow gives the opportunity to employ the VQA ansatz by connecting with the knowledge of quantum physics much more easier. And our ansatz that we are interested is in the form of quantum quench dynamic. So what is quantum quench dynamic? The quantum quench dynamic is the dynamic that we change the parameters suddenly over an interval, and we call the number of the interval is the number of quenches. And the Hamiltonian that governs the system that we are interested is the disorder acting spin chain with homogeneous longitudinal field and disorder transverse field. And this kind of Hamiltonian can realize to phase of matter by sampling the on-site transverse field from an interval determined by disorder strain W for the small limit of W compared to the interaction J. In this regime, the system will be in the tumuli phase, where the interaction generates the entanglement across the system, resulting in a chaotic dynamic, and that is the local observable will convert to tumor value. However, if we are in the another regime where the disorder governs the system compared to the interaction, the system will be in the many-body localized phase, where the disorder prevents the system to tumularize and the entanglement grows slower than the tumuli phase. And in this regime, the initial state, after it involved, it will retain some kind of memory. Okay, so to associate the notion of phase of matter to our VQA ansatz, we initialize the ansatz in two ways. So we're enforcing our Hamiltonian to correspond to either Tourmaline phase or MBL phase. So this means that we draw the parameter from the same interval for each initialization, but the parameter will be different in each quench. And then we just study the expressivity and the trainability of the answer. And yeah, so we are now in the middle of this presentation, and Sukana just asked me to put the test, and yeah, and he said it's going to be fun. Yeah, that's all. Okay. Okay, we can continue with our talk. So the first aspect that we study is the expressivity. So the expressivity measures how close the answer ensemble is to the Hahn distribution, and we relate this to comparing between the output state ensemble to the Potter-Summa distribution. So we just kind of like ask whether our state is typically random in the Hilbert space or not, and then we compute the KL divergence. So as a result, we plot between the KL divergence for the two initialization against the number of quenches. And what we observe is that for both initialization, it reached the maximal expressivity with if we have enough number of quenches. Also, if we carefully look at the way it converts, we can see that in initialization, it requires a smaller number of quench for the output state ensemble to cause the Potter-Summa distribution. And this reflects the nature of chaotic dynamic in the Tourmaline phase. Okay, so the second aspect that we study is the Barren plateau, as the expressivity is a desired feature in the problem agnostic answer, but it also gives us the problem known as the Barren plateau. So the Barren plateau is just the flat landscape where the cost concentrate around the mean, meaning if you calculate the variance of the cost, it scales exponentially decay with the number of qubits. And intuitively, this is because the curve of dimension, as we trying to compare two vectors in a pure manner. So by pure manner, I mean we are trying to compare the two vectors that is too randomly or like it lies in very large space by having a high integrating answer or having like the high expressive answer or even like implement it in noisy hardware and use global measurement. To avoid one of the factors of the Barren plateau, we compute the variance of the local observable. So we compute the variance of C1 and C2, and then plot it against the number of quench. And it's quite get the similar result to the KL divergence, where the saturated variance saturate into the same value with the tumulized initialization exhibit a faster decay. And also, if we carefully look at the saturated variant and then plot it against the number of qubits, it also shows like the exponentially decay of the variance. So that is the emergence of Barren plateau in our answer. And yeah, this can be also explained in the context of the dynamical Lie algebra, as the Lie algebra, the real dimension of our Hamiltonian is scaled exponentially with the number of qubits. Okay, so, this one is, sorry for this topic. Actually, I'm gonna show the correspondence between the KL divergence and the variance and also the entanglement by plotting the number of quench when these three convert to some value. And this gives some kind of like this correspondence between three of them. So if our answer is maximally expressive, it means there is Barren plateau, and it also means that because the dynamic generate entanglement so that it reaches the maximal entanglement. And this also connects the notion of phase ohmmeter, because Tourmaline phase and many-body localized phase have different entanglement entropy behavior to the VQA performance. Okay, so building up on our result, we categorize the regime of initialization into three regimes based on the saturation onset in each initialization. So for the first regime, it is the regime before the saturation in the thermalization initialization. And in this regime, both initialization are free from baryon plateau, but it is inexpressive. However, in the regime 3, after the saturation in the MBL phase, in this regime, both initialization has maximally expressive, but it entered the baryon plateau regime, so we cannot train it at the first step. However, if we look at the second regime here, in the between regime 1 and regime 2, and if we initialize our ansat in the MBL phase, we could have like a large variant compared to the thermalized initialization, and with the saturation of the KL divergence in thermalized initialization, it also gives us a hint that in this regime it has sufficient number of parameters, so that after we train the parameter, it exhibits the MBL phase, and it's some kind of like we can reach some unitary in this regime. Yeah, so in this regime, they have like 2 benefits that I talked before. So it's guaranteed not to suffer from baryon plateau and has sufficient large number of parameters. Okay, and again, if we look at the part before, and we look at the difference between the number of quench when there is saturation in the MBL and thermalized, we can see that the width of the regime scale linearly with the number of qubits. Okay, so this is quite like the end of my talk. I want to emphasize that our ansat that we study is a problem agnostic ansat. So its performance may vary depend on the problem that we are trying to solve. And also in our work, we didn't consider the classical similar ability, and there is no analytic result. But for the latter case, we suggest that we can use the thing that called local integral of motion to solve some analytic result, and then we can say something about classical simulatability. And lastly, for the extension of our work, we suggest to explore more phase-off method and put it in our framework, so we can see something new about connecting phase-off method to the analog one. And also, we can explore more variety of the model. This one is not, there is no archive yet, but yeah. So we can like change the interaction length or change the Hamiltonian, something like that. And yeah, so it's just summary, we just propose a regime where MBL initialization can have benefit in like have a large variance and can have sufficient number of parameters. And yeah, we can smile, maybe. Thank you for your attention.
Thank you very much. Questions? I have one there.
Thanks for the very nice talk. So you mostly looked at baryon plateaus. Did you look at local minima at all in this middle regime?
Yeah.
So, if you go back a slide in this middle setting.
So you...
Did you look at local minima at all? Like, do you have okay local minima in this setting, like when you do this initialization strategy?
So actually, we just say that on average, we're going to have like large gradients, so it's not that local minima, I think.
Okay, thanks.
Yeah.
Other questions?
Thanks for the talk. Just a curiosity, have you tried to see what happens in the edge of the phase transition?
Sorry, like if we shoot the W so that it is in the phase transition?
In the edge, like in the intermediate region between many body and thermalization. I expect, I don't know,
Well, I mean...
intermediate behavior, but did you try to look at it?
I think if I understand correctly, in our implementation, we use the finite site, so there's no like a cut off like the phase transition, and this have like.
And in this region, have you tried to see what happened?
Well, I think it's gonna. I mean, I'm not sure about that actually. For if we change the W so that it's not in the MBL phase, right? So that you asked me correctly.
Okay. Thank you.
Maybe we can talk later.
Yeah, sure.
To move on, but maybe we can take the other question while the next speaker is setting up.
Thank you for a very nice talk. I was wondering, how do your optimizer hyperparameters influence the slope of the behavior between the MBL and the other phase?
So sorry again.
So you have these two phases, one that converges very fast and one that converges slowly. I am wondering if hyperparameters of your optimizer had some effect on this convergence speed.
So you wonder if there is some other hyperparameter that affect this, maybe like the interaction between the spin, something like that?
Yeah, or if
Yeah.
you are, when you are updating your theta's, there is some size of the update step, like the optimization part itself.
Maybe we can talk later.
Yeah, okay, we can discuss later.
Sorry.
Thank you for a nice talk.
Thank you again. Let's thank the speaker.